In this lecture, we shall discuss about the surface energy of a liquid, angle of contact when a solid is dipped into a liquid, capillarity action, and then finally determination of surface tension. Now, what is surface energy of a liquid? If W is the work done against the surface tension of the surface of a liquid to increase area delta A, and the increased area is, let us suppose this is delta A, then the surface energy is defined by this E, which is W divided by delta A. Now, the unit of the surface energy. And unit of surface energy is the unit of work divided by the unit of area. So the unit of work is, we know this is joule, and the area is meter square, so is joule per meter square, which is equivalent to Newton meter, and then meter per meter square, and which is equal to Newton per meter. Now we see that the unit of surface energy of a liquid is the same as the unit of surface tension of the liquid. We can now define the surface energy in the amount of work done to increase the surface area of the liquid through unity under isothermal condition. That is, potential energy per unit area of the surface is called surface energy. Now, factors affecting surface tension of a liquid. surface tension depends on temperature. Surface tension decreases if the temperature of the liquid increases. Second, medium above the liquid. Surface tension depends on the medium touching the free surface of the liquid. Third, pollution. Fourth, presence of soluble material in the liquid. And the last, fifth one, electrification. Surface tension depends on the medium touching the free surface of the liquid. For example, if the water surface is in contact with air, then the surface tension of the water is 72 into 10 to the power minus 3 Newton per meter. However, if vapor is present above the water surface, then the surface tension becomes 70 into 10 to the power minus 3 Newton per meter. So you see the effect of medium above the liquid. Now pollution. If oil or fat floats above the liquid, then its surface tension decreases. Presence of soluble material. If some material dissolves in the liquid, then its surface tension changes. If inorganic material such as common salt, sodium chloride dissolves in pure water, then its surface tension increases. But if organic material dissolves, then its surface tension decreases. And in the case of electrification, if the liquid is electrified, then its surface tension decreases. Now we discuss about angle of contact. Let us draw a figure. There is a container and there is a liquid inside it. For simplicity of presentation, we consider this is water, and we have another container here, and in this container we have mercury. This is also a liquid. Okay. If a solid substance is immersed in a liquid, as we have shown here, it is seen that at the point where the liquid touches the solid, here and here, the liquid does not remain horizontal like other places. Rather, the free surface bends either upwards or downwards. Here, downwards or upwards. It is observed that in case the liquid weights the solid, for example, water and glass, here is a glass rod and this liquid is water, the liquid surface actually rises. On the other hand, when the liquid does not weight the solid, for example, mercury that we have shown here, mercury and the solid glass rod, the liquid surface falls a bit. You see here and here. If a tangent, you see CA, is drawn from the point of contact C here, so if a tangent CA is drawn from the point of contact C of the liquid with the solid to the curved liquid surface, then the angle made by the tangent with the solid surface CB, this solid surface CB inside the liquid, is called the angle of contact. Theta is the angle of contact. So we can define angle of contact this way. The angle between the tangent to the curved liquid surface at the point of contact and the solid surface inside the liquid is called the, so inside the liquid is called the angle of contact. For a given pair of solid and liquid. Now the liquid that weight is solid, for example water and the glass, the angle of contact becomes acute or less than 90 degree. Here theta is less than 90 degree, but here theta is greater than 90 degree. For glass and pure water, the angle of contact is about 8 degree. The liquid that do not weight a solid, for example, as I have shown here, the mercury and the glass, the angle of contact becomes obtuse, greater than 90 degree. For glass and pure mercury, the angle of contact is 139 degree. The angle of contact depends on the following factors: nature of solid and liquid, the medium above the free surface of the liquid. For example, if there is air above mercury, then the angle of contact between mercury and glass will be different than if there is water above the mercury. Purity of solid and liquid. If the liquid is not pure, and or if any other material is present at solid surface, then the angle of contact changes. The angle of contact between pure water and clear glass is nearly zero. But if even a small oily material is there in the glass, then the angle of contact increases. Okay, now we discuss about capillary action or capillarity action of liquid. When a tube with a very small radius, say for example, I'm now drawing here. So we have a liquid here, for example, water. So a tube having very small and uniform area of cross section is known as a capillary tube. If an end of a capillary glass tube for example like this, so if this a capillary tube with a very small radius glass tube is immersed in the liquid, then some liquid rises or falls from the free surface inside the tube. So in the case of water here, water will rise in the capillary tube. Okay, and similarly, if we consider mercury instead of water as the liquid, and if we immersed a glass tube, capillary tube with small radius, then this kind of things will happen. This is mercury here. So if an end of a capillary glass tube is immersed in the liquid, some liquid either rises in the case of water, and and some liquid will fall in the case of here mercury. The liquids which wet the glass tube, example water, for them the free surface of liquid inside the tube rises above the free surface of liquid of the outside vessel. The liquids which do not wet the glass tube, in the case of mercury here, for them the free surface of the liquid inside the tube falls below the free surface of liquid of the outside vessel. The phenomenon of rise or fall of a liquid in the capillary tube is known as capillarity action. So we can define capillarity action. Phenomenon of rise or fall of a liquid in the capillary tube is known as capillary action. Okay, by this capillary action, we can determine the surface tension of a liquid. Okay, this is the last topic today's lecture. Okay, determination of surface tension of a liquid. We have a liquid here, and it will be better if we delete this to show the direction of the forces acting here. Okay, actually we we can redraw this. Okay, listen carefully. It is seen that if a capillary tube is immersed vertically in water or in liquid, when the liquid weighs a solid, say for example a glass tube, the liquid rises a little inside the tube and the surface becomes concave. You see here the surface becomes concave. Let the angle of contact between the liquid and the solid be theta. The radius of the tube where the liquid surface touches the tube be small r. Small r is the radius of the glass tube, and let us suppose T is the surface tension of the liquid, and theta is the angle of contact, and we consider a liquid like water where the angle of contact is acute angle, that means angle is less than 90 degree. The height of the lower point of the liquid surface inside the tube from the liquid surface outside the tube is small h. So this this height is small h. Small h, height of the liquid column inside the tube. Let the density of the liquid be rho. Now, if you see the tangent, the surface tension will act, along this direction. So, if a tangent is drawn from the inside wall of the tube and the point of contact of the liquid to the curved liquid surface, then the surface tension would act along the tangent inward. The circumference of the capillary tube is twice pi r, which is the length of the line of the liquid which touches the inner wall of the tube. As a result, the wall of the tube will experience an inward force of magnitude twice pi r into t, because twice pi r is the length, and it will act along the tangent. That force will act along the tangent. According to the Newton's third law of motion, the wall will exert an equal and opposite force twice pi r into t. And this force will be just opposite to the inward force. If this force is resolved into two perpendicular components, one is along this direction, okay, this is twice pi rt, so this will be cos theta, and this one will be twice pi rt sin theta. And this one is also twice pi rt sin theta. So this one and this one horizontal, these components will be cancelled out, and we will be left with only the vertical component twice pi rt cos theta. And this twice pi rt cos theta and this upward component of the force due to the surface tension will be balanced by the liquid column inside the tube. That is the total. To find the mass of this is we can write down this volume into density. This is mass. So the volume of the water column, liquid column inside the tube is pi r square into h, and there will be a small volume because of the the curved liquid surface here, and that one we have shown this is the liquid. Okay, we'll have to add to this, and let us say this volume of the liquid, this portion is Vc. So this is the volume, and if you multiply the density, so this is mass of the liquid column, and if you multiply by the acceleration due to gravity, you will get the weight of the liquid column, which will be balanced, and this will act along the downward direction, and the force component due to the surface tension, and this one will act along the upward direction. So this will be balanced. Now we'll have to find this, and from this relation we can calculate the T, the surface tension of the liquid. Now we'll have to calculate this Vc. This Vc will be, you see if we find the volume of this portion, this is a part of a cylinder, and then if you subtract this volume, we will get then the Vc. So the volume of the cylinder ABCD is pi r square into this is this pi r square, and this is also the height is r, so pi r square into r, and then we'll have to subtract, and this is half, and the volume of the sphere with radius is smaller, so is 4 by 3 pi r cube. So if you simplify this, we'll have this pi r cube. This is 1 minus 2 by 3. So this one will be 1 by 3 pi r cube. Okay, so this is Vc. Now if you substitute this Vc, this expression here, then we can rewrite this relation. twice pi r t cos theta, and this is pi r square h plus now 1 by 3 pi r cube and 2 rho g. So if you take common pi r square, then we'll have here h plus r by 3, and this is rho g. So the expression for the surface tension T becomes okay, 1r from left hand side and 1 from right hand side will be cancelled out, so will be r rho g divided by twice cos theta and into h plus small r divided by 3. So you see from this formula we know the radius of the glass tube. Rho is the density of the liquid, g is the acceleration due to gravity, theta the angle of contact we can measure, h is the height of the liquid column. So we can apply this formula and calculate the surface tension of the liquid. One word I should actually mention here, the tube, the upper portion on the upper surface of the liquid inside that tube, this is curved and this is known as meniscus. Okay, so this for some liquid like water, this theta is very small. In that case, we can substitute cos theta equal to 1, and the expression of capital T will be further simplified expression. Some phenomena relating to surface tension. There are many phenomena that can be explained in terms of surface tension of liquid. Okay, this is the end of this lecture. In the next lecture, we shall discuss about fluid dynamics. In particular, we shall study the equation of continuity of fluids and the Bernoulli equation. When fluid moves, then we'll have to consider this fluid dynamics.